Hi, this is a pictures of two rendering model that use two different rendering technique. So the one on the right, you see that the grass, the land is very realistic and the lighting is better. The metal part is shiny, look like a real metal. The right one is used PBR. PBR is a correction of the rendering technique that have underlying theory very close to the physical world, and it also aimed to mimic light in a physical way that look more realistic compared to the original writing technique without any tweak or hack. This is the equation of the PBR. I will go in detail. They just show the equation first. The lighting model that consider PBR have to follow three conditions here. The first one is it had to be on the microprocess surface model. The second one is it had to be energy conserving. And the third one is it had to use the physical bed, BRDF, which is the bidirectional reflexive distribution function. All of the PBR technique use the microprocess model. It is a theory that describes any surface using the tiny little tiny reflection mirror and at the surface. The left surface gonna have a chaotic alignment of the microprocess, and the light gonna get scattered and it have a bigger area of reflection. The smoother one can have the smaller area but sharper. The halfway vector is a vector between light and view vector, and the equation is here. We use it a lot to see the alignment of the microprocess. And in the picture that show what I just talked about, the one on the left have the very low roughness value. You can see the area of the reflection is small but sharp. The one on the right, it have full roughness. The second condition is it had to be energy conservation, which means that the light energy that outgoing have to not exceed the incoming one. When the light go to the surface, it have separate to two parts. The part that absorb into the body and the part that reflects away. The one that absorb into the body is called refraction part. Is make the diffuse light, and the one that reflect away is called specular lighting. We also separate material into two types, the metallic and non-metallic, which called the dielectric. Before talking about the third condition, I want to talk about the rendering equation. And one of them is the very smart one, and the one that physics-based that rendering is strongly follow, is the reflection equation. It is the equation that I showed at the beginning because it is a very important equation. Radiance with the symbol L is the quantity of the magnitude or the strength of the light that coming in the same direction. And here on the left is the strength of light that coming out and is what we want to find. The one on the right is the strength that come in. And this also the important one is the area of projected shape on the surface. It is called solid angle. Here, the area A in the picture and it have the normal in. So when the area become very small, the area become point P, and also the solid angle, which is the area, it become direction vector. And see here, normal and the vector, which is the cos theta here in the picture. So when the cos theta, the theta is very small, mean the light is almost perpendicular to the surface. It's gonna be the highest strength of light. So now we know almost everything about equation except F value, which come up to the third condition that all model that gonna be PBR have to be the physical base BRDF, which is the bidirectional reflective distribution function. And there are several the BRDF out there, but the most popular and almost all real-time PBR rendering pipeline used is this one. It's called the Cook-Terrace BRDF. The Cook-Terrace BRDF have two separate parts. The first part on the left is the reflected or diffuse part. KD is the ratio of the light energy that gets reflected. F function Lambert is a C over pi. C is a diffuse surface color, and divide by pi to make the diffuse light normalized. And this one is a little bit harder. Ks is also the ratio of the energy of light that get reflected. Cook-Terrace function have three functions inside D, F, G. D is the normal distribution function, F is Fresnel equation, and G is geometry function. And the denominator is just the normalization factor. The normal distribution function approximates the relative area of the microfaucet that align exactly with the half-wave vector, the microfaucet model that I talked about in the beginning. And for when the roughness is low, highly concentrated microfaucet align with the half-wave vector, so it make it concentrate and have a very bright spot radius. When the roughness is high, there are randomly scattered. There are more microfaucets that align with the half-wave vector but not concentrate. And here is a normal distribution function equation, which I'm not going to go in detail. The geometry function approximates the relative surface area where the microsurface detail overshadow each other and make the layer of light occluded. And the left surface on the right is more overshadowing, so it makes the surface is more dimmer gray. On the left is smooth, so it's more white and bright. This is the equation of the geometry function. I'm gonna skip it. The Fresnel equation here is very important. It is the ratio of the light that get reflected over the light that get refracted. It's very hard to pronounce, so I type it down here. The value also depends on the angle that we look at the surface, and also the type of surface it is. And here the H half-wave vector and the V is view vector is powered by 5, so it's a lot. And also the F1, it depends on the surface. No, not F1, F0. It depends on the surface. And so if the surface that have F0 high is start with a high value and the total is 1. So here is the value. The water is 0.02 and it's going up to diamond 0.017, but for the metallic it start with very high 0.56 ion, and the silver is 0.95, so it's almost 1, so it start with almost max. So after we get the Finel equation solved. Now we get both sides of the Cook-Terrace equation. The both side is the diffuse part and the reflect part. So we get the F of the Cook-Terrace BRDF, and we go to the main equation, reflectance equation. We get the F, and this is the final equation that we use to calculate the physically based rendering. I was planning to use this equation that I just talked about to do the demo, but the demo is just not working. So I gonna end the presentation here. Thank you very much. Goodbye.